additive identity, and then multiplication should be associative. We also have distributivity, and then they are including unito. But we know that more generally, we don't expect our rings to be unito. Okay, so that's what we looked at yesterday. Question, yes. When we, sorry? Semi-rings are contained in modules. Monoids. Semi-rings are contained in monoids. If every semi-ring a monoid, no. Is every semi-ring a monoid? Semi-ring. Is every semi-ring a monoid? Every monoid is a semi. So we need semi-ring, they are not assuming unito. Yes. So for them, semi-ring, we only have actual associativity. Yeah, so they are adding associativity to a magma, so they are assuming closure and associativity. So when we add on the identity, that's when they tell us it's a monoid. So if is every semi-ring a monoid? You want a ring? Is every ring a monoid? Sorry? Is every ring a monoid? Yes, because the ring has the, but also remember for the monoid we need to ask ourselves, under which operation? Yes? Yes, so it's indeed a monoid. The ring is a monoid, for example, under multiplication. It's a monoid. And when we, actually it's even more, because for the additive part we even have a group, isn't it? Yeah, so it's much more. Yeah. Is every semi-ring a monoid? Definitely not. But every monoid is a semi-ring. Yes. That what is a subcategory of semi-rings? Yes. Semi-ring is a subcategory. I understand what you mean, because we had something on subcategories, isn't it? Yeah? I know. So, supercategory, subcategory, where are you exactly? Sorry about that. Are you on supercategory or semi-category or subcategory? So in this case, we see groups is a subcategory of semi-groups, isn't it? Because a group, I mean, we add axioms to a semi-group to have a group. So a group is indeed a semi-group. So let's try to add, to put here. What did we want? Semi-rings. Okay. I just wanted to edit this. Okay. So we want semi-rings. Semi-rings, semi-groups. Remember, we have semi-rings and semi-groups. For the semi-ring, we are good. Because for semi-ring, what we are really violating is the, isn't it, the distributivity. Try to check the axioms for semi-rings. Semi-rings, semi-groups.
She's talking about a semi-ring.
Then in that we are good. Let's see. So we need, what we need are semi-rings. We need, is it a subcategory of, Cherry's gonna complain about that. A subcategory of monoids. Monoids. Let's see what it gives us. It's true.
But if you ask, is it in? Is it a noun? Is it
semi-ring in, because now in this case, we are not compare, okay. So the thing is now you're comparing different structures. So for semi-rings we have addition and multiplication, remember, yes? And then for the monoids we have only one operation. So, or just a star. So in this case, let's try semi-rings in. Semi-rings in monoids. That's false. That's false. Semi-rings in monoids. Let's see. So what's the missing link there? What's the missing link? I think it's more like, I think the missing link could be garbage in, garbage out. Like we want to try out. So I think how they gauge subcategories and supercategories, there is already something inbuilt, yeah? So possibly when we write semi-rings is in monoids, I don't know, it's doing something which we don't know, most likely. Because when we try this, for example, if we have already a specific group or ring, we are good. Yeah? So we need maybe to understand this in, yeah? So is it used, because there is somewhere where we talked about parents, I don't know if we mentioned it yesterday, that, for example, Z, like there are parents and categories. So there are times where we have to use a parent is in a category. So there is a ranking. I'm sorry, we didn't talk about that. We have an element, we have a parent, and a category. Yes? So the parents, for example, that's where we can have a ZC. And then the category is where we can have rings, and then the element, anything. Yes? So in each case, something is going on. Something is implemented. So we can ask it something based on what we want, but most likely it's following another thing. Yeah? Yeah. Okay. So for example, if you want to know the parent for 1, maybe for 2, it already knows the parent for 2, yeah, integer ring. But then I would also want, another person can say, but I want the parent for 2 to be QQ, isn't it, yeah? But that's not what it's doing. For it, it has a parent, an original parent. So that's maybe the confusing part. Yeah? Because it is something inbuilt, so that's where the problem is. Okay. So can we try the matrices before the polynomial rings? Should we start with polynomial rings or matrices? Matrices. Perfect. Okay, what's this? So we have matrices, matrix rings and linear algebra, and we tried this yesterday. Okay. So we tried this yesterday, that if I want, for example, if I want my 2 by 2 matrices over Z, yes, our usual rings, it can be any ring, it can be anything. We said in that case you want a full space, yes? So what do? Now our M is a matrix space. Of what? Our base ring is Z. But remember, in Sage, our Z is ZZ. Our complex are CC, our reals are, and our rationals are QQ. Yeah, so, and then the dimension, so we have a 2 by 2. But if we wanted a 2 by 4, in that case we'll have 2, 4, isn't it?
2 by 4.
A 2 by, sorry? So if you want the matrix space of all 2 by 4 matrices over the integers, in this case it will be 2, 4, exactly. But if it's 2 by 2, we don't have to write a 2. Yes? Yes. Then we get our matrix space. And remember we said even for the vector space, it's exactly the same, not the same, similar command, vector space. Vector space, but in this case we said we can't have a vector space over the integers, it has to be a field. And we put the dimension, 3-dimensional vector spaces over that. Okay, so that's what we are doing there. So when we run, we've already run this, we see that this is a matrix space of 4 by 4 matrices. Okay. Then, just like any ring, we can check several things. Yes? We can check several things. Is the ring commutative? Is the ring Noetherian? Is the ring, which other property? Athenian. Do we have Athenian? You have to implement Athenian. Yes. So is the ring Athenian? Is it any property we can think of? Yes? Is the ring semi-prime? Now, let's try to check semi-prime. So the thing with, so you know, we have our original characterizations, the basic ones. Noetherian, commutative, and then there are those that arose from research. Maybe someone did research and came up with a notion, morphic. Reduced. So in that case, it's the responsibility of a person working in that area to implement that particular thing. If it is catching, someone will do it. For example, we have these integer valued polynomials. I work in integer valued polynomials, but since it's a catching topic, one has already implemented it. Yes. So what am I supposed to do in that case? Implement the new things, but one has already implemented that ring. Yes. So any terms we come up with, that is research opportunity for us to implement those things in Sage Math. Yes? Perfect.
Does it mean that there are some things that are not in the Sage Math, that are not implemented in the Sage Math?
Many.
So that means you may not actually do anything with Sage to change them.
You can do something by implementing them. Yes.
So it is open for research.
Yes. So that's why Carol was asking us yesterday that, okay, we have already something inbuilt, it's prime. Yes? Why do I have to hassle again to define is prime, go through it, yes? Why are we doing that? Because you come across some things or you work on some things that you want to implement yourself. So when you get to know at least how it's done, you can do it. Yes. So that's the reason for the hassle. It's prime and so on. Okay. Yes. So remember, our matrix is commutative. Our matrix is usually commutative. We had an example. Not always commutative. Yes? Question? Not always. Remember yesterday we had AB not equal to BA. isn't it? So even here, when we run, we already know that it's false. Yes?
So the case of multiplication,
Yes. So, yes. Actually, like for the categories, when you go back here, even if we don't go back, let me just insert. So remember we had, let's say, rings. Because it's not a category. Okay, that's what we had. So one thing we see here, we have additive associativity, additive commutative, and so on. Where we see only associative, they're already implying multiplication. Yes? So whenever we talk about commutative without what? Without adding additive or anything, we are referring to multiplication being commutative. Yes, so that's what I wanted to. And remember we said we can even add something. But since he has mentioned it, let's try to add commutativity on that and see what it gives us. It's returning an error. Could anybody know why it's returning an error? Yeah, because it was little c. Okay, so when we add commutative to rings, what is it giving us? Commutative rings now, yes? Because when you see these, we already see that we are not assuming commutativity. A ring is not necessarily commutative. No, yes, no. Yes, so when it's commutative, we are referring to, for all AB, yes, for all AB in that ring, AB must be BA, exactly. Yeah, so that's what we're referring to here. Okay, so when we add on commutative, it will give us a category of commutative rings. Like we said, we can add on several things, even finite and so on. Then we'll find finite commutative rings and so on. Yes? Okay, that was a by the way. So let's go to, so when we run our commutativity, it is saying, why is it saying, okay, so what was the mistake? Because I jumped from this cell, I hadn't ran this cell, yes? And then it wasn't recognizing n, yeah? So even in the file, we need to go step by step. If I hadn't run this, still it would not give me, yeah. Now, did I run this? Yes, I ran it, and it's that, okay. Okay, so is it an integral domain? Are our matrices integral domains? Are our matrices integral domains? Are our matrices integral domains? No. Which axiom is violated? Which axiom is violated? Already commutative. Integral domains, we assume commutativity. Then another thing, we also assume the non-existence of zero divisors, isn't it? We know that in matrices we have zero divisors. We did look at that. Yeah. In matrices we have zero divisors. We know it. Yes? We can have two non-zero matrices that give us 0. Yes? This is true in matrix rings. So we have zero divisors in matrix rings. So we expect this to be. Still, it's bringing an error. Why? Because I didn't run, but I ran it. Yes. So what does that mean? It is saying matrix space with category object has no attribute is integral domain. So what does that mean? That is not yet implemented. Or you have to call something, those who work with Python or what, you have to call something. Maybe mathpy and so on, yeah? Let's check the integers. In case we have ZZ, is it an integral domain? That's true. Why? Because someone has already implemented that, yes? For the matrices, something has to be done. You either have to implement it or you have to call some package from somewhere. Yes? So if I check our basic rings, you will see that they are actually integral domains. Yes? Yes. All our basic rings. Now let's try integer. Okay, CC is definitely an integral domain. So let's try other rings to see if they are already implemented. Let's say ARA is integers modulo anything, right? Because when it's modulo 2, it's a field, so most likely it's going to give us, okay, 8. Modulo 8. Let's put 8, thank you. Because we are sure it's not. Okay, so then we are going to check if ARA is indeed an integral domain. Hopefully someone implemented it. Yes? So that's already implemented because they are our usual rings. So this is not an integral domain because we know they are zero divisors. How come we know they are zero divisors? Yesterday we got idempotence. I'm sorry that I'm taking you so much into ring theory. Yesterday we saw that we have idempotence in that ring, and idempotents are always zero divisors. Oh, perfect. Yes. Am I so fast? Perfect. So for this case, but when we change to 2, because we know for any prime, integers mod prime are fields, yes? So when I change to a 5, I will automatically have that this is true because I'm in a field now. Yes. Okay. Have we tried this? List all the matrices in the matrix space of 3 by 3 matrices over a field of 2 elements. Can we try that? And then find the number of elements there. Let's find the number of elements there as well. if we have integral domain, that is not recognized because it is supposed to be small integral domain. Yes? Yes, so we have to check such errors. How many elements are there? How many elements do we have? How many elements do we have? How many elements do we have? Over a field of two elements. Yes, sorry about that. So it's not an arbitrary field, but a field of two elements. Yes? Over a field of two elements. An example of a field of two elements? Integers, isn't it? Yes. So we have integers, and we know how to get that. But that's just one example. Do we see that? That is our notation. I hadn't shared that. So GF, that's a field, a finite field of size 2. So that's a field of two elements. If I want a field of three elements, because yes, in this case we have a field of two elements, yes? And if we are mod 3, we have a field of three elements. But you can have a field of 4 elements, yeah? So in this case, if someone asks us a field of 4 elements, then that's problematic. Can we try? So this will give us a field of 3 elements, for which we have an example, integers mod 3, right? But that is also a field of, those are 4 elements actually. Yes? And these are copies of Z2. Yes? Yes. So if you try to find a field of 6 elements, let's see what it will tell us. It will return an error. Because finite fields, the order is a prime power. Yes? Yes. So it's telling us the order of a finite field must be a prime power. Yes, that's the error it's returning. So if we try G, a finite field of 10 elements, it will return the same error. But I'm good to say a finite field of 9 elements. Yes, so in general, what you have in your matrix as the ring is GF2, more generally. Are we good? Perfect. It has how many? 512. Perfect. Can you try to create the matrix space? So we have our M, And we said it's the matrix space over a finite field, yes? Of 2 elements. What's the odd dimension? 3 by 3. So the dimension is 3, yes? And then we return our M. Yes? So that will tell us it's a full matrix space of 3 by 3, dense matrices over a finite field of size 2. Yes? Is it possible to see the elements there? Can we try to visualize the elements? Can you try to see the elements there? The question we ask is to see the number. It's a list, so we can always get the number of elements. We are first of all getting the number of elements there. So there are 512, yes? And then we can also, what more can we do? We can list.